Hello, my name is Christian Aparicio, and in today's tutorial, we're going to optimize the core in a curved composite panel. We're going to be using Nastran's optimizer to perform today's optimization. Now, when you're working with composite optimization, it can be a very lengthy process. So instead of making this tutorial 1 or 2 hours long, I've actually broken up the tutorial into different phases, if you will. In this first phase, we're only going to be focused on optimizing the thickness of a constant thickness core. So here we're on phase B. And what I want to do is establish a baseline result. If our entire core was a constant thickness, I wanted to determine what the optimal thickness is in this scenario. In phase D, this is where we're going to have the core vary in thickness. We're going to have a new thickness, maybe T2, a new thickness here in the middle, T3, and then here on the far right, maybe a new thickness, T4. This is where we're going to perform our variable core thickness, if you will. Now, before we ever get to phase D, the final workshop, we first need to run a topometry optimization that tells us where the core should be thickest to handle or to prevent buckling. And here are some results of that topometry optimization. Here I'm getting told that the core should be really thick here, and in this entire region that you see here, it might be a good idea to have a core span in these different sections of the curved composite panel. And this is the expectation in this workshop. We'll start off with the mass of about 6, and we'll reduce the mass to about 4. At the same time, we'll make sure that the buckling load is always greater than a 1.0. So here you'll see what the starting thickness is first. And in this workshop, again, we're assuming that the core has a constant thickness throughout. So here, we're going to have a certain thickness at the beginning, and then by the end, we're going to have a new constant thickness, T2, I'll call it. Now, for this model, we're going to clamp the core or the composite panel on this edge, and then we're going to have a load applied on the opposing edge. One thing I've done in this example is the following. Number 1, the element normals are going to be pointing in this direction. The next slide has a long explanation on why the element normals are purposely pointed in this direction, so I'll leave it up to you to read that description. Another thing that I've done, this model is symmetric. And what tends to happen with symmetric models is that if your loading is somewhat symmetric also, if you were to reverse the load, so here I'm drawing the load as if it was reversed, you'll actually get negative buckling load factors. So as an example, let's suppose that your first buckling load shape maybe looks like this. And then this is going to be kind of hard for me to replicate. Let's suppose the eigenvalue was positive 100 for this example. In fact, if you were to reverse the load, you would get a buckling load shape that would be symmetric. So here, let me try to draw a symmetric buckling load shape. So here, the buckling load shape might be negative 100. This tends to confuse a lot of users, but just know that it's because of this. Your model is symmetric. The loading is somewhat symmetric. So you'll actually get buckling load shapes that are symmetric also. So that's why you're getting these positive and negative buckling load shapes. But what I've done in this example, I've updated the eigenvalue entry so that the eigenvalues are limited to being positive, i.e. the lower bound is 0. So throughout this whole workshop, I'm only dealing with positive buckling load factors or eigenvalues. Let's see, what else is there to discuss here? Right, okay, let's go ahead and talk about the optimization problem statement. As always, please take a few moments to draft out the problem statement for your own composite model. Draft out the variables, draft out the the objective and the constraints. This is critical for successful optimization. Here, the goal or the variables, actually, we're going to just optimize one thickness. So I'll call it TI for now. Or rather, we're going to represent the thickness of the core as X1. We're going to let the thickness range between 3 and 25 millimeters. We don't want fractional values. For example, we don't want 3.19999 millimeters. We want either 3 or 4 millimeters. So we're going to specify discrete values between 1 and 30 millimeters. Now, since the pcomp entry, here I'll draw out the pcomp entry. Since we're using the symmetry option in the pcomp, and I'll say sim, we're only going to define, or rather, X1, the thickness, is only going to represent half the total core thickness. So here, when you see this 3 for the lower bound, that means that the lower bound of the total core thickness is going to be 6 millimeters. And then the upper bound is 25. So this means that the total upper bound thickness is going to be at most 50 millimeters. And right now, the core thickness is 2 times 10. So the current thickness of the core is 20 millimeters. So just know that relationship as I go through this example. We're going to try and minimize the weight while making sure that the buckling load factor is greater than 1.0. So before going and getting started, as always, you're more than welcome to contact me regarding this tutorial or any other optimization tutorial you might see in my large cache of tutorials. If you want access to the Sol200 web app or any other tool in today's presentation, please let me know at this email address and I'd be more than glad to reply back to you. So let's go ahead and get started. Let me go ahead and jump out of here and go to the web app. So go to the user's guide and navigate to the composites tutorial section. This is where you're going to find the tutorials for this curved composite panel, and we'll go ahead and click on the link starting PDF files. And we'll go ahead and extract the contents. So this is our starting curved composite panel. You'll notice that the current thickness of the core is 10 millimeters here. But remember, since we're using the symmetry option, the actual thickness of the core is 40 millimeters. It might actually help to open the viewer web app. So with the viewer web app, you can actually display the thickness of your plies and your core. So let me actually show you what that looks like. So we'll go ahead and upload that first bulk data file. And then we'll go ahead and open the model display panel. And then we'll go ahead and display our different plies. So right now, each layer is going to get its own unique color. But many times we want to color the plies and layers depending on the angle of the layer. So we'll go ahead and click on this icon that says a color of detail. And then if we zoom out a little, you'll see that the core now has this beige color. And then you'll notice that the 90, 45, negative 45, and 0 degree plies, they get their own colors. And remember, this composite is symmetric. So in the pcomp entry, we're only defining half the layers. And then Nastran internally is going to build the other half. So even though we define the core to be 10 millimeters, the actual core has a thickness of 20 millimeters. Okay, now let's go ahead and configure the core thickness optimization. So for that, let's go ahead and open the optimization web app. And we're going to go ahead and upload this bulk data file of the curved composite panel. So let's go ahead and select that bulk data file. And we'll look in the variables section and click on size. And out of all the possible settings we can set as variables, we only want to look at the thickness properties. So let's go ahead and search for thickness. And this is, or rather layer 1 is ply 1, layer 2 is ply 2, and so on and so on. The core layer is going to be the 5th layer, so we'll go ahead and press on that icon to set it as a thickness variable. Now here we'll set the lower bound as 3 and the upper bound 25 millimeters. And remember, we only want to go in increments of 1 millimeter. So we'll go 1.0, 2.0, so on and so on through 30. And then we'll go in increments of 1.0. And then, as always, all the necessary bulk data entries are automatically created for me here on the right. So the core thickness is going to start off with 10 millimeters. It's going to range between 3 and 25 millimeters in increments of 1 millimeter. Now, for the objective, we want to minimize the weight. Now, for the constraints, let's look for the buckling load factor. We'll click on the plus icon to create that response. Typically, we are only concerned with the first buckling load. If you were interested in working with natural frequencies, you would go to the normal mode set of responses, and then you would create these various frequencies. Here you would say, okay, natural frequency 1, natural frequency 2, 3, and 4, and then you would configure your bounds. But here we're only dealing with the eigenvalues / buckling load factor. And here the lower bound is 1.0. Let's go to subcases. Now, the thing about a buckling analysis is that it's actually going to require a so-called multidisciplinary optimization. So what do I mean by this? In SOL 105, the first subcase is a statics subcase. The second subcase is the buckling subcase. We have to go here and specify that. So to do this, go to Options, Multidisciplinary Optimization. Mark this checkbox. For subcase 1, say that the analysis is statics. For subcase 2, say that the analysis is buckling. Mark or assign the buckling constraint to subcase 2. Now, internally, you'll see that subcase 1 has a statics analysis, and then if you look at subcase 2, the analysis is buckling. So be sure to do this. Let's go ahead and go to the exporter, and let me quickly look at my notes just to make sure I haven't adjusted the settings. Okay, so we're going to go and use the default settings, so leave everything here the same. Let's go to the exporter, and let's go ahead and click on download bulk data files. And then while that's happening, I'm going to go ahead and get another viewer web app open. And I'll go ahead and rename this file core thickness optimizations. So let's go ahead and do that right now. To core thickness optimization. And we'll go ahead and extract the contents. And then we'll go ahead and double click that to start the optimization. So here in this viewer web app, let me go ahead and start preparing some of this models. What I want to do is I want to show you a comparison of before and after. So we'll go ahead and set this up right now. And then we'll go ahead and let the optimizer do its thing for the next few moments. Okay, so the optimizer is pretty much complete. Let's go ahead and look at what the new results are. So we see a few things. Number one, the mass of this composite panel has been reduced. So here, before we started off with the mass of about 6 times 10 to the negative 4, and then we end off with the mass of about 4. Remember, we're only dealing with half the thickness of the core right now. So half the thickness of the core started off with 10 millimeters, and then it ended off with the thickness of 5 millimeters. So we started off with the core thickness of 20 millimeters, and we end off with the new core thickness of 10 millimeters. Now, to do a comparison, let's go ahead and open this other viewer window. Let's navigate to the workspace B directory, and we'll select that file, and we'll click upload. And in a moment, we'll go ahead and look at what the new core thickness is. So let's go ahead and display that, and we'll color this. Okay, so if I look at it from before and then look at it after, you'll see that the core thickness is thinner, which is good. This was the goal of this whole workshop. The whole goal of the workshop was to minimize the weight while making sure we satisfy the buckling load factor constraint. So this is going to serve as a baseline for future workshops. So let me go ahead and open a new PowerPoint file. And what I'm going to do here, I'm going to create a new table. And then I don't know how many rows I'll need yet. Okay, so the starting design had a thickness or a mass of 0.6, and maybe I should put it here. The maximum buckling load, or the buckling load factor rather, was 3.36. So we'll go ahead and document that here. And then if you want to confirm what the buckling load factor is, you have a few options to do that. If you look in the F06 file, and if you scroll to the very bottom, if you look here in this section called responses in design model, you'll get various tables. You'll get a table for the weight response, and you'll get a table for the buckling load response. You'll see that the value is actually 1.06. So let me copy this. And is this right? Am I looking at the right data? Right. Okay. Yes, I am. So let's go ahead and copy that new buckling load factor, and then let's copy the new weight. So this is a core thickness optimization, and then here's the current mass, and this is the buckling load factor, and all abbreviated BLF. So later on, we'll go ahead and do a variable thickness optimization. So you'll see that in the third part of this whole workshop series. So this is the end of this baseline core thickness optimization. We're going to use these results to compare future results with. And then I'll end that off with my contact information. As always, any questions, comments, feedback, if you want access to today's tools, please feel free to contact me at this email address. Thank you so much for watching.